Your favorite basis should be the standard basis of Rn. But why? Take R2 for example. We can draw these two vectors. Notice how they're perpendicular and length 1. That's a pretty nice property. Any vector in R2 can be written like this. It's incredibly easy to find the coordinates. This isn't the only basis of R2. Here's another one. We can draw these vectors. Once again, they're perpendicular and have length 1. However, it's seemingly much more difficult to write coordinates of this vector. That's where inner products come into play. We're going to make finding coordinates in B' almost identical to finding coordinates in B. An inner product, defined like this, is a bilinear function so that 1. The inner product of u and v equals the inner product of v and u. The inner product of a scalar times u and v is the scalar times the inner product. 3. The inner product splits over sums. 4. The inner product of a vector with itself is positive and is 0 only if the vector was 0. This holds for all u, v, w, and v, and scalars lambda. Properties 2 and 3 are the bilinear part. Property 1 is only true for real inner products, which is all we do. For complex inner products, there's a complex conjugate after the equal. The fourth is perhaps the most interesting and useful property, as it implies that an inner product can act as a length. The standard example of an inner product is the dot product in Rn. If u and v are vectors in Rn, then the inner product of u and v is the dot product of u and v, which is u times v transpose, or the sum of coordinate-wise multiplication, or u1 v1 plus u2 v2 up to un vn. This is fairly straightforward to prove. You just follow the definition of an inner product. Let's go back to the basis b and the vector ab. I'm going to pretend like I didn't know the coordinates and just say they're c and d. I want to find c and d. In the old days, we would set up a matrix and reduce. However, as you may have suspected, we can define inner products on general vector spaces, where matrices may either not make sense or might be infinite. We want a better way to find c and d. Let's use an inner product. Take the inner product of a and b with 1, 0. Plug in what a and b equals, distribute everything. The inner product is bilinear, so distribution holds. There's a reason we use the word product. The inner products are easy to compute, and we're left with c. We know c is the inner product of ab with 1, 0, which we can also compute. It's equal to a. And surprise, a is equal to c. This really shouldn't be mind-blowing. Now how about b'? The coordinates are much more difficult to find. We could reduce this matrix, but that doesn't really look fun. I want to try the inner product trick from before. Take the inner product of a and b with the first basis vector. Plug in the coordinates and expand. Evaluate the inner products, and we get c. This says c is just the inner product, which is very easy to calculate. For example, find the coordinates of the vector 3 minus 2. It'll be this. How did I do it so fast? I just did two inner products. Each coordinate is the inner product of 3 minus 2 with the corresponding basis vector. I also did my work off screen. I can't do this in my head. I mean, come on, this is a video. Not like I'm sitting here writing this out live and on the fly. I'm scripting this stuff and editing. These videos don't just magically appear. It's not like they just come from nowhere and you just watch them. These two bases, b and b', have two really nice properties. The vectors were perpendicular and length 1. Let's generalize these notions. Vectors v1 and v2 are orthogonal if the inner product of v1 and v2 is equal to 0. In Rn, we would say these vectors are perpendicular. For polynomials, perpendicular may not make sense. A vector is normal if the inner product with itself is equal to 1, or it has length 1. In general, the norm, or length, of a vector is norm of u equals the square root of the inner product of u with itself. This square root makes sense due to the fourth property of inner products. Here's an example. Find the length of u equals 1, 2. Draw a picture. We have a triangle with side lengths 1 and 2, so we can just use Pythagorean theorem. And the length is the square root of 1 squared plus 2 squared, or the square root of 5. We didn't use an inner product, we just used what we already knew. Will the inner product give a different length? What if the lengths are different?
It was at that moment that Dr. Mitch had an existential crisis.
No, the inner product won't be different. Just compute it and we get the square root of 5. You can even look at the form and see it's Pythagorean theorem. Finally, a basis b equals v1 up to vn is orthonormal if distinct vectors are orthogonal and all the vi's are normal. The bases b and b' from earlier are orthonormal. This turned out to be the key property that makes that inner product trick work. If v is a linear combination of the vi's, Then the coordinate AL is the inner product of V with VL. Just compute it. Plug in A. When you distribute, the inner product will be 0 unless the two basis vectors are the same, so this simplifies to AL. Keep in mind this only works if the vectors v1 up to vn are orthonormal. If they aren't, everything breaks.